Hello, I'm Ruslan Nikolaev from Virginia Tech. In my talk, I'm going to present Librettos, a dynamically adaptable multi-server library. This work is done jointly with Mincho San and Binoy Ravindran. The mythic design used in general-purpose operating systems today is often inadequate. First, it lacks isolation for core kernel components. Fail recovery capabilities are also very limited, and a very large underlying trusted computing base is a fertile ground for security attacks. These problems are addressed by the microkernel design, specifically in multi-server operating system design where core components run in isolated user processes. Aside from these issues, performance can also be a concern because applications may want to have more direct access to the underlying hardware resources. Kernel bypass libraries and library OS improve performance by eliminating unnecessary OS layers and providing more direct access to hardware. In this work, we argue that multiple OS paradigms such as multi-server and library OS seamlessly integrated in the same OS are desirable. First, applications may have specific requirements, like some applications may be more performance critical, some applications may be more security oriented. But regardless of this, we want to share the same driver code base. We don't want to rewrite code, we want to retain POSIX compatibility. And finally, because of limited physical hardware resources, we want to efficiently use them. For example, if an application requires high performance, we want to give it direct access. But when our load decreases, maybe we want to give direct access to some other application. And for that reason, dynamic switching between library and multi-server OS mode is very desirable. Consider the following example of a server ecosystem. We have a number of applications such as Python, NFS, rsyslog, Java, the NTP time synchronization server, SSH. And those applications are not very performance critical in this example, but if some failure happens in some network components, we want to transparently restart it without rebooting the entire system. For that reason, network server is very desirable, as shown in this figure. But then also we have some other applications, such as database, HTTP, which may be more performance critical, and it makes sense to give them direct access to hardware. In this work, we use Rump kernels and the Rumprun unikernel. The concept of Rump kernels was introduced by Antti Kanti and the NetBSD community. It effectively means that NetBSD code was largely refactored to so-called any kernel components, which can be used in both user and kernel space. Specifically, in NetBSD, we may want to use user space for testing or debugging the device drivers. But when development is complete, we may want to run it in the kernel space. The Rumprun unikernel uses any kernel components to effectively create a library OS. So in this figure, we see that the Rumprun unikernel have any kernel components. Then there is also so-called Rump kernel glue layer, and it replaces system calls with regular function calls. So there are certain advantages of Rump kernels and the Rumprun unikernel. They are very flexible, and they use most of the NetBSD code, specifically drivers, which are very important, as well as the user space environment. The Rump kernel part is already upstreamed and maintained by the NetBSD community. It also uses a permissive license to close BSD license, which is very important for some applications because Linux licensing terms can be quite restricting in some cases. But there are also some disadvantages. The Rumprun unikernel right now lacks SMP support. It also lacks Zen HVM support. The unikernel model itself is also quite limiting, and we may want to have a more general OS model. We propose the libretto design, which is based on the Rumprun unikernel. So we add SMP and Zen HVM support as the first step in the Rumprun unikernel. That allows us to reuse NetBSD device drivers and user space environment just like in the original Rumprun. We run Rumprun instances on top of the Zen hypervisor. Although we are not limited to some specific hypervisor, we can also use microkernels. And then we also propose to have a more advanced OS model. So in our prototype, we implement the network server, and applications can talk to network using this server, but they can also use direct access, like they can directly access NIC or NVMe, and they can finally dynamically switch between these two modes at runtime with no interruption. To understand how Librettos works, let's discuss its architecture. First, we have microkernel and hypervisor layer. In our case, it's Zen. It runs its own scheduler, and the hypervisor allocates vCPUs per each virtual machine. And each virtual machine is going to run its own application or server. So let's consider first example with direct mode applications. Direct mode applications will have NVMe and NIC drivers which directly talk to the corresponding hardware. Then also this application has an end-to-end scheduler which allows to run any number of threads on top of fixed number of vCPUs. Then we also have the network server, which has the NIC driver, and NIC driver talks directly to hardware using PCI pass-through capabilities, and other applications that use this network server will talk to it through the IPC channel. So, like application 2. Application 2 has a special so-called virtual interface. And the goal of this virtual interface is to talk to the network server. So our network server is quite low level, and by that we mean that it handles L2 frames. Consequently, TCP runs in the application address space itself. And that has certain advantages. For example, we can have a full recovery if the network server fails, because all TCP state is inside the application. As long as TCP doesn't time out, we can fully recover. It also allows us to accommodate two paradigms easily, and dynamic switch also becomes quite feasible. Our network server uses fast IPC based on Zen-specific capabilities such as shared memory or virtual interrupts. We also use lock-free queues. So the network server shown in the middle has a shared memory regions with applications, and the shared memory regions contain lock-free RIN buffers, RX and TX, and their goal is to exchange MBUFs. So when an application one wants to transmit some packet, it will issue a virtual interrupt, and network server, when it receives some packet, it also will issue the corresponding virtual interrupt to the application. And RIN buffers will contain packets. So our network server is quite low level, and some knowledge from high level protocols is also needed. In our case, we handle TCP and UDP. To that end, we have a so-called Portmap table. The Portmap table is kept in Zen. So whenever an application wants to bind some TCP or UDP port, it issues a port bind hypercall. And the port bind hypercall allocates a corresponding entry in the Portmap table. Total size is 64K entries for TCP and 64K entries for UDP. So that this Portmap table can be accessed directly from the network server, because the network server just maps corresponding pages to its address space. And whenever it needs to transmit a packet, the network server can just consult the Portmap table and figure out what application this packet needs to be forwarded to. So now let's discuss dynamic switching and how it works with our network server. So applications that don't need a dynamic switch, they just use network server and share the same IP address. For example, application 1 uses IP1, and any application that is going to use network server in a regular way, they will use IP1. But if some applications wants to potentially have a dynamic switch, they request a dedicated IP address. So initially, application 2 behaves the same way as application 1. It has its own virtual interface and it just talks to the network server. However, when a dynamic switch happens, the network server deactivates IP2, and this IP address is configured on the corresponding physical interface on the side of application 2. So then, consequently, some ARP invalidation happens, and all new packets will go to this physical interface. So, and finally, if applications just need to have direct access, they don't need an intermediate virtual interface. They can just directly use corresponding physical interface. We evaluated Librettos on a 20-core machine with 10 gigabit Ethernet and NVMe. We run Zen 4.10.1 and compare against Linux 4.13 and NetBSD 8.0. So NetBSD 8.0 is also used for Librettos itself. And we also enable jumbo frames. So first we measure the overall network throughput using a popular NetPipe ping-pong benchmark. For various sizes, we measure the corresponding throughput, and all systems show pretty much comparable performance, like Linux, direct access mode, Librettos, server mode, Librettos, NetBSD. The only exception is the original Rumprun power virtualized Rumprun, which is very slow in this case. So we also to evaluate NVMe performance, we run NFS server. We execute a file bench CSI from the client machine, and we have a direct access to NVMe and direct access to NIC. NVMe is initialized with XT3, and we have mixed tile load. So Librettos in this test outperforms Linux and NetBSD, and the reason is because Librettos avoids system call overhead, which is known to be have a substantial overhead sometimes. To evaluate network applications, we also run Nginx HTTP server. We measure Nginx performance for various levels of concurrencies and various block sizes. And Librettos is better for smaller blocks because, again, system call overhead may be non-negligible for smaller blocks. But as block sizes becomes larger, Linux shows some benefits. However, Librettos is still faster than NetBSD. And one reason why Linux has some benefits is probably because Linux has more performance optimizations than NetBSD, and this which is especially evident for 10 gigabit Ethernet. But we hope that at some point in the future this gap will be reduced and NetBSD will have a closer performance to Linux, and consequently Librettos will also have better performance. So we also tested dynamic switch with Nginx for smaller block sizes such as 8 and 32K, we set concurrency to 20, and we also have a hybrid baseline. Hybrid baseline is basically we have 50%, we spend 50% in direct mode and 50% in server mode. As you can see from this figure, Librettos is better than Linux, let alone NetBSD. And the hybrid mode is better than just plain server mode, and yet it doesn't use exclusively hardware resources all the time. So we also tested Memcached with read-dominated workloads and binary protocols. We found that Librettos performance is very close to that of Linux. Librettos server performs a little worse than direct access, and NetBSD has the worst performance. So it's somewhat similar performance we observe, somewhat similar trends we observed for Redis, where we also see some gaps between NetBSD and Linux, and this gap is much larger here. And consequently, Librettos is also worse than Linux in some cases. So that may be just related to the specific application and how it works with BSD, specifically NetBSD systems. Finally, we evaluated and tested failure recovery. We have two cases. One test, we have one application when Nginx uses network server, and there is also parallel file system activity. So when the network server fails, file system activity still continues. So we have a second case where we have Nginx and Redis. Nginx uses direct access, Redis uses server mode. When one application fails, the other is not impacted, and the other way around. So Librettos shares similar goals with other systems, such as multi-server operating systems like Minix Free, LNOS, QNX. Specifically, failure recovery and isolation is the same goal in these OS designs. Multi-server approaches are also used in informatic systems in Sawmill, Virtuos, and Snap. Kernel bypass libraries, just like Librettos, achieve direct access to hardware. DPDK and SPDK are very commonly used libraries. LibreOS approaches are also quite common. IX uses DPDK, but it's not compatible with POSIX. Arrakis is somewhat compatible, but is built for Barrelfish OS, for which device driver support is limited. Finally, there are some unique kernels such as UKL, a recently initiated effort by Red Hat. Their goal to replace DPDK and SPDK with Linux-based unique kernel. We already achieved this goal with a more general multi-server LibreOS design. So to reiterate Librettos aspects, we want to say that it supports two models, multi-server and LibreOS modes. It's the first OS design that seamlessly integrates two models in the same operating system. We share the same driver base. Applications don't need to be modified. So it's also possible to have a dynamic switch. Application can switch from the network server to direct mode with no interruption at runtime. And our prototype solves a number of technical challenges. We add SMP support and Zen HVM support to Rumprun. Librettos is publicly available at librettos.org. Thank you very much.